To understand the origin of the solar system, we must first deconstruct the idea that space is empty. The nothingness from which we came was actually a gigantic structure called a molecular cloud. Imagine a region spanning light years, composed of 99% gas, hydrogen and helium, and 1% microscopic dust. For millions of years, this cloud remained static due to a physical concept called hydrostatic equilibrium. This means that the gravity of all particles which tried to pull the cloud inward was perfectly cancelled out by the thermal pressure of the gas, which pushed outward. For planets to be born, this stalemate of forces needed to be violently broken. The rupture of this equilibrium did not happen spontaneously. It required an external trigger. The most accepted theory today, corroborated by the presence of specific isotopes found in ancient meteorites, is that a supernova exploded in the galactic neighborhood. When a massive star dies, it ejects its outer layers at supersonic speeds. The shock wave from this explosion traveled through the vacuum and struck our stagnant molecular cloud. The impact did two crucial things. First, it enriched the cloud with heavy elements, iron, silicon, oxygen, forged in the dead star, the basic ingredients for rocks and living beings. Second, and more importantly, the shock wave created regions of high density. In these regions, compressed by the shock wave, gravity won the war against pressure. Once a pocket of gas reaches a certain critical mass, it enters a process of positive feedback. The more it contracts, the more gravity it generates, which pulls in even more gas, increasing the contraction. Gravitational collapse became inevitable. What was once a diffuse and cold cloud, with temperature close to absolute zero, began to fall in on itself in free fall. The gravitational potential energy, the energy of the position of particles, began to transform into kinetic energy, motion, and thermal energy, heat. As material fell toward the center of this collapsing region, the density increased exponentially. However, this collapse did not occur in a perfect straight line. Because the cloud's original turbulence caused particles to have random movements, the total sum of these movements resulted in a slight net rotation. It may seem like a small detail, but in the physics of the universe, a small initial rotation in a body that is drastically shrinking has catastrophic consequences for its final shape. The core of this cloud, now spinning and heating, became the protostar. But the rest of the material, the dust and gas that did not immediately fall into the center, became trapped in orbit. The spherical cloud was about to undergo a radical geometric transformation, dictated by a fundamental law of physics that would explain why all planets today are aligned. The initial collapse had ended. The structuring phase was about to begin. With the cloud rapidly collapsing toward the center, the law of conservation of angular momentum came into play. This law dictates that in a closed system, the amount of rotation must remain constant. If the size of the system decreases, the rotational speed must increase proportionally to compensate. It's the same physical principle that makes a skater spin faster when pulling their arms in. In the case of our nascent solar system, a cloud light years in diameter shrank to the size of the current solar system. The result was a dramatic acceleration in spin speed. This accelerated rotation created a powerful centrifugal force, which began to fight against gravity. But here's the detail that explains the system's shape. Centrifugal force acts mainly in the direction perpendicular to the rotation axis, at the cloud's equator, pushing material outward. At the poles, however, there is no centrifugal force, only gravity pulling downward. This created a flattening effect. Material at the poles fell freely toward the central plane, while material at the equator was held in orbit by the rotation. The result of this process was the transformation of the spherical cloud into an accretion disk, or protoplanetary disk. Imagine a spinning pizza dough. The force stretches it sideways, but leaves it thin in the middle. In space, this process was aided by inelastic collisions. Particles of gas and dust orbiting at different inclinations collided with one another. These collisions canceled out vertical movements, up and down, but preserved the average rotational motion. Over time, this orbital friction forced virtually all matter to align into a single thin, organized plane. It is for this mechanical reason that today, if you look at a model of the solar system, all planets, from Mercury to Neptune, orbit the Sun practically in the same plane and in the same direction. It wasn't an accident. It was an imposition of the physics of collisions and conservation of motion. This disk became the factory floor for planets. The density of matter in this disk increased drastically compared to the original cloud. What were once solitary atoms floating in a vacuum were now grains of dust constantly colliding. However, the disk was not uniform. At the absolute center, the density was so extreme that matter could no longer orbit. It was crushed. The protostar at the center continued to accumulate mass, sucking up 99.8% of all available material in the disk. The friction of layers of gas falling onto the star generated hellish temperatures. The engine of the solar system was being assembled, but the vital spark was still missing. The center was hot, but it was not yet a true star. The pressure needed to reach a breaking point to change the nature of matter forever. At the center of the disk, the protostar reached a critical limit. The accumulated mass generated such intense gravitational pressure that hydrogen atoms in the core were squeezed to infamous distances. When the temperature exceeded the mark of 10 million degrees Kelvin, the electrical repulsion between protons was overcome. Nuclear fusion occurred. The Sun turned on, ceasing to be a body that merely radiated residual heat from compression to become a self-sustaining fusion reactor, converting matter into pure energy. This ignition generated a shock wave of radiation and charged particles known as the solar wind. In the first millions of years, this wind was much more violent than it is today, the star's T Tauri phase. It acted as a cosmic vacuum cleaner, sweeping away the volatile gases, hydrogen and helium, that still remained in the disk. But the effectiveness of this cleaning depended on distance. This brings us to the most important concept for understanding planet formation: the ice line, snow line, or frost line. The ice line is the thermal boundary of the solar system. Near the newborn Sun, the heat was too intense for substances like water, ammonia, and methane to remain in solid state. They sublimated, turning to gas, and were blown away by the solar wind. Therefore, in the inner region of the system, where Mercury, Venus, Earth, and Mars are today, the only solid material available to build planets was metals and silicates, rocks, which have extremely high melting points. This explains why the inner planets are small and rocky. There was little solid material available, as most of the mass, the ices and gases, had evaporated. On the other hand, beyond the ice line, located approximately between the current orbits of Mars and Jupiter, the temperature dropped enough for water and other volatile compounds to freeze. Out there, the disk was full of dust grains and ice crystals. Because ice is much more abundant in the universe than rock, the building bricks available in this outer region were far more numerous. This allowed planetary cores formed there to grow much faster and become much larger than their inner cousins. This thermal distinction created two radically different construction zones. In the hot zone, construction was slow and limited to rare materials, stone, metal. In the cold zone, construction was accelerated by the abundance of ice. The stage was set for the next phase, accretion. But how to turn microscopic dust into rocks kilometers in diameter without them destroying themselves upon collision? The physics of agglomeration was about to be tested, and the result would define who would survive in the inner combat zone. With the newly ignited Sun bombarding the system with heat and solar wind, the protoplanetary disk ceased to be a homogeneous mixture. It became an environment segregated by temperature. This segregation created an invisible but physical boundary located about 3 to 4 astronomical units from the Sun, between where Mars and Jupiter are today. Astronomers call this boundary the ice line or snow line. Understanding this line is understanding why the solar system has two classes of citizens, the rocky dwarfs and the gas giants. Inside the ice line, in the Sun's neighborhood, temperatures were too high for volatile compounds like water, methane, ammonia, and carbon dioxide to exist in solid state. In these regions, these substances sublimated instantly, transforming into vapor that was largely dispersed by solar radiation or remained in gaseous state, unable to cluster together. The result was a scarcity of building material. The only elements that could remain solid and form stable dust grains were metals, like iron and nickel, and silicates, rocks, which have extremely high melting points. The problem is that in the chemical composition of the universe, metals and silicates are relatively rare. They make up less than 1% of the total mass of the original nebula. This imposed a severe limit on the growth of the inner planets. No matter how much time passed, there simply weren't enough bricks available in this hot region to build anything larger than Earth or Venus. The inner planets were doomed from birth to be small, dense, and dry, limited by the lack of heat-resistant solid raw material. However, when we crossed the ice line toward the exterior, the scenario changed drastically. Out there, far from the scorching heat, the temperature dropped below 150 Kelvin, 120 degrees Celsius. In this cold, water and other volatiles instantly froze into grains of solid ice. Since water is composed of hydrogen and oxygen, two of the most abundant elements in the universe, the quantity of ice bricks available was immensely greater than the quantity of stone bricks. This meant that beyond the ice line, the density of solid material in the disk was 3 to 4 times greater than in the inner part. The protoplanets born there didn't have to settle for just rocks. They could aggregate vast amounts of ice into their structure. This allowed their cores to grow much faster and reach colossal masses, on the order of 10 times Earth's mass. This extra mass was crucial as it gave these cores sufficient gravity to capture light gas, hydrogen and helium from the disk before it dissipated, transforming them into the gas giants we know. The ice line didn't just divide materials, it divided destinies. With the construction zones defined by the ice line, the solar system now faced its greatest mechanical challenge: how to transform microscopic dust into planets. In the beginning, the disk was full of micrometric particles, similar to smoke or talcum powder. The physics of agglomeration at this initial stage is relatively simple and governed by electrostatic forces. When these tiny grains collided gently, they stuck to each other due to van der Waals forces, the same principle that makes dust bunnies form under your bed. Through these gentle collisions, the dust grew, forming fluffy and porous clusters of a few centimeters. But here, the process encountered a formidable obstacle known to astrophysicists as the meter barrier or bouncing barrier. The problem is velocity. As these clusters grow, they begin to experience aerodynamic drag with the disk's gas, which alters their orbits and increases collision speeds. When two rocks the size of a soccer ball collide at speeds of hundreds of meters per second, they don't stick. The impact energy is too great for electrostatic forces to hold them, and the gravity of these small objects is irrelevant, practically zero, to keep them together. The result expected by classical physics would be mutual destruction. The rocks should shatter and return to dust, or simply bounce off, the bouncing barrier. In theory, growth should stop at objects about 1 meter in size. If it depended only on simple collisions, planets should never have formed. So how did we overcome the meter barrier? The answer lies in a phenomenon called streaming instability. Instead of relying on individual rock-against-rock collisions, the protoplanetary disk developed collective behavior. The gas in the disk didn't rotate at the same speed as the solids. Due to gas pressure, it rotated slightly slower. This caused solid pebbles to feel a constant headwind, which tended to cluster them together. Imagine cyclists in a peloton. Those in the middle experience less air resistance and can ride together more easily. In the disk, dense clouds of pebbles and rocks began to form spontaneously due to this fluid dynamics. Within these dense pelotons of rocks, the local density of solids increased drastically to the point where the collective gravity of the swarm came into play. Suddenly, it was no longer necessary for rocks to stick by contact. The gravity of the rock cloud became strong enough to collapse the entire swarm at once. In a rapid process, clouds of meter-sized boulders gravitationally collapsed to form, Instantaneously, objects 10 to 100 kilometers in diameter, the planetesimals. The solar system skipped the difficult growth phase, from meters to kilometers, by cheating the collision rules through collective gravity. With kilometer-sized planetesimals formed, the individual gravity of each body was already strong enough to attract more material. The barrier had been broken, and the race to form planetary embryos was officially open. If you could time travel to about 10 million years after the Sun's birth, you wouldn't find the orderly solar system of 4 rocky planets, Mercury, Venus, Earth, and Mars, that we see today. Instead, you would find a chaotic and overcrowded war zone. Where today there exists a vast void between Earth and Mars, there were dozens, perhaps even 100, planetary embryos. These were worlds the size of the Moon or Mars, orbiting dangerously close to one another. The formation of the inner system was not a process of elegant design, but a brutal process of natural selection, known in astrophysics as oligarchic growth. The term oligarchic is used because in this phase, a few large bodies, the oligarchs, dominated the disk's dynamics, feeding on smaller bodies. Thanks to the breaking of the bouncing barrier that we saw earlier, trillions of kilometer-sized planetesimals served as food. The gravity of these larger embryos functioned as a trawl net, pulling toward themselves everything that passed nearby. Growth was exponential. The larger the protoplanet became, the greater its gravity, and the more material it stole from neighbors. But there was a spatial limit. The inner system is small. There was enough material to create a few large planets, but there were too many mouths wanting to eat. The fundamental problem was orbital stability. When you have 50 to 100 objects with planetary mass crammed into a narrow region around the Sun, mutual gravitational interaction becomes an agent of chaos. Each time a protoplanet passed near another, they exchanged orbital energy. Small gravitational tugs, accumulated over millennia, began to elongate orbits that were once circular. Orbits ceased to be safe parallel lanes and became ellipses that crossed each other. The system transformed into a busy highway where cars suddenly decided to ignore the lanes and drive diagonally. The result was inevitable: giant collisions. And we're not talking about asteroids falling to the ground. We're talking about entire worlds colliding with other worlds. At speeds of tens of thousands of kilometers per hour, these collisions had enough energy to instantly liquefy rock and merge two bodies into one, or shatter them completely. It was a period of cosmic cannibalism. The 4 planets that remain today are literally the survivors who devoured their siblings. They grew upon the graves of the other 90 embryos that didn't make it, and the first forensic evidence of this massacre is hidden orbiting dangerously close to the Sun. The strange case of Mercury. To witness the birth of the first planet, we need to travel to the most dangerous region of the solar system, the inner edge of the protoplanetary disk, just 58 million kilometers from the nuclear furnace that is the Sun. Here, physics and chemistry operated under a tyrannical regime of heat. While in the outer regions dust was a rich mixture of ice, carbon, and silicates, here near the fire, the temperature of almost 1,000 degrees Celsius vaporized everything volatile. There was no water, no gases, no organic compounds. What remained was a cloud of resistant particles, composed almost entirely of heavy metals, iron, nickel, and refractory rocks. It was in this environment of scarcity and metallic purity that Mercury began to be born. The accretion process here was frantic. Due to the proximity to the Sun, the orbital period was very short. The year lasted a few weeks. This meant that metallic dust particles crossed paths and collided with dizzying frequency, much greater than in Earth's or Mars's orbit. Within millennia, gravity and electrostatic forces transformed this shining dust into a swarm of iron asteroids. As these asteroids merged to create proto-Mercury, the first chemical magic occurred: planetary differentiation. The young planet was so hot, heated by incessant impacts and the decay of radioactive elements like aluminum-26, that it became a bowl of liquid magma. In this ocean of molten rock, The physics of density took command. Iron and nickel, being heavier, plunged toward the planet's center, forming a gigantic metallic core. Silicates, lighter rocks, floated to the surface, forming a thick mantle and primitive crust. At this stage, Proto-Mercury was a normal planet. It was twice its current size and had a healthy proportion between rock and metal, much like Earth's. If the story had stopped here, Mercury would be just a smaller, hotter sibling of our planet. But the primitive solar system was not a place of peace. It was a cosmic pool table played by giants. Mercury's drama is explained by the hit-and-run theory. The most modern computer simulations show that during the chaotic phase where dozens of planetary embryos fought for space, Proto-Mercury was targeted. Another protoplanet with about 20% of Mercury's mass crossed its orbit. But due to the dizzying orbital speed near the Sun, almost 50 kilometers in, the collision didn't result in a smooth merger. It was a violent and surgical glancing blow. The kinetic energy released in the impact was sufficient to instantly vaporize Proto-Mercury's crust and most of its rocky mantle. Imagine removing an orange's peel with an explosion, leaving only the core. Trillions of tons of vaporized silicates were ejected into space. The iron core, dense and compact, survived the shock almost intact. Anywhere else in the solar system, this debris would have eventually fallen back to the planet, as happened in the formation of our moon. But Mercury was too close to the intense solar wind of the young star. The radiation blew the cloud of vaporized rock away before gravity could recover it. Mercury was left naked. The planet we see today is essentially the exposed iron core of a world that was once much larger. This explains its physical anomaly. It is a metal ball with a 20,400 kilometers radius, where the core occupies an absurd 85% of the volume. Mercury is the survivor of a planetary assassination attempt, an iron scar orbiting the Sun. Moving away to a safer orbit, about 108 million kilometers from the Sun, we find Venus's construction zone. Here, the temperature already allowed silicate minerals, the common rock you step on Earth, to exist in abundance, along with metals. With many more bricks available than Mercury, Venus grew quickly and voraciously. Its accretion followed the classic model: planetesimals colliding, merging, and creating a gravitational field strong enough to begin holding gases. During its first millions of years, Venus and Earth were indistinguishable. They were identical twins separated by only 40 million kilometers. Both underwent differentiation: iron core, rock mantle. Both had intense volcanic activity and, crucially, both developed oceans. Yes, isotopic evidence suggests that young Venus was a blue world. Water, brought by asteroids and comets or degassed from the planet's interior, condensed to form shallow, warm seas under a cloudy sky. There were, most likely, conditions for life. So why did Venus become today's sterile hell while Earth flourished? The answer lies in a tragic combination of orbital mechanics and atmospheric dynamics. First, the traumatic event. Venus spins backward, retrograde motion, and incredibly slowly. A day on Venus lasts 243 Earth days, longer than its own year. The physical explanation for this oddity is, again, a titanic collision at the end of its formation. A planetary embryo the size of Earth likely struck Venus head-on against the direction of rotation, canceling its angular momentum and reversing its spin. This slow rotation had a fatal consequence. It shut down the planet's internal dynamo. Without rapid rotation in the liquid iron core, Venus couldn't generate a protective global magnetic field, the magnetosphere. Without this magnetic shield, Venus was at the Sun's mercy. And the Sun was changing. As the star aged, its luminosity increased. The Sun is 30% brighter today than it was at the beginning. The habitable zone moved outward. Venus's oceans began to warm. Evaporation increased, filling the atmosphere with water vapor. Water vapor is a powerful greenhouse gas. More retained heat caused more evaporation, creating a positive feedback cycle called runaway greenhouse effect. The oceans boiled entirely. The atmosphere became a pressure cooker, and here the final blow was delivered by chemistry. Ultraviolet radiation from the sun. Unfiltered struck water molecules H2O and 2XTH2O in the upper atmosphere, breaking them apart. Hydrogen, light and with no magnetic field to hold it, escaped into space. Oxygen, reactive, descended and combined with carbon and sulfur, creating the dense atmosphere of CO2, X-2CO2, and clouds of sulfuric acid. Venus didn't just die. It was mummified by its own atmosphere. The surface pressure today is 90 times Earth's, enough to crush a nuclear submarine. The temperature is 470 degrees Celsius, day and night. Venus serves as nature's ultimate warning. Planets are not static. They evolve, and the line between a blue paradise and a lead furnace is frighteningly thin. If you went back 4.6 billion years in time, Earth's orbital position harbored nothing resembling a blue planet. There was only a region of the protoplanetary disk slightly cooler than Venus's, but still too hot for ice to survive. There, a mixture of silicate dust, metals, and some residual gases circulated, all remaining from the sun's formation process. This is where Earth is born, not from a single block, but from billions of fragments in constant collision. The first phase was planetesimal accretion. In the future Earth's region, solid dust grains, mainly silicates and iron, collided gently, forming pebbles, then rocks, and finally blocks kilometers in diameter. These bodies, called planetesimals, were numerous and orbited the Sun in slightly different trajectories. Each time two of them came close enough, gravity began to deflect their orbits, increasing the probability of collision. When they collided, most of the time they merged, growing. Thus, from a sea of orbital boulders, a handful of larger bodies began to emerge, the planetary embryos. As some of these embryos gained mass advantage, we entered the phase called oligarchic growth. In this phase, few bodies dominate the region. One of these embryos, located approximately 1 astronomical unit from the Sun, began to grow faster than the others. It was proto-Earth. Its increased gravity transformed it into a kind of vacuum cleaner, sweeping up planetesimals in its vicinity. Each impact converted kinetic energy into heat. The surface of this young world was not solid. It was an ocean of magma. Young Earth at this stage looked more like a faded star than a welcoming planet. This intense heat had a crucial effect. It allowed differentiation. Proto-Earth's composition was not homogeneous. It mixed iron, nickel, silicates, and traces of radioactive elements. In liquid state, the densest materials, mainly iron and nickel, sank toward the center, forming the metallic core. The lighter silicates floated, forming the mantle and primitive crust. It is in this phase that Earth gains its layered structure, with a dense core that would later become the engine of our magnetic field. At the same time, the planet released gases trapped in minerals: water vapor, carbon dioxide, nitrogen, sulfur. This degassing built a thick primordial atmosphere, dominated by CO2, X-2CO2 and vapor, without free oxygen. The image of Earth here is that of a ball of molten rock wrapped in suffocating fog. The Hadean Aeon, named in reference to Hades, the Greek underworld. It's important to note, up to this point, Earth remains essentially dry on a planetary scale. There are traces of water, yes, but far short of global oceans. Then enters the water paradox. Wookiee, according to the temperature conditions of the disk's inner region, Earth should not have received large amounts of ice during its initial construction. The minerals that formed it are the type that form in dry and hot environments. However, today, we have oceans with a total mass equivalent to about 0.02% of Earth's mass. Something difficult to explain only with water original to the nebula. The solution to this paradox comes from outside. While Earth was consolidating, the gravity of Jupiter and other giants began to disturb more distant regions, especially the outer part of the asteroid belt. There lived bodies rich in water in the form of ice mixed with rock. carbonaceous asteroids. Unlike comets from even more distant regions, these asteroids have a chemical water signature ratio between normal hydrogen and deuterium that matches our ocean's water. This suggests that they, not comets, were the main suppliers. When these asteroids' orbits were perturbed, many were sent on eccentric trajectories to the inner system. Earth, still hot and frequently struck, became the target of intense bombardment. Each impact vaporized part of the projectile, releasing water and volatiles into the atmosphere. Over tens of millions of years, this rain of wet asteroids added significant amounts of water to Earth's surface. At the same time, Earth's interior remained active. Volcanoes expelled more water vapor from the mantle. The combination between water coming from outside, carbonaceous asteroids, and from inside, mantle degassing, inflated the atmosphere with vapor. But the surface was still too hot for water to remain liquid. A cycle of condensation and re-evaporation formed in the upper atmospheric layers. Over time, however, Earth began to lose heat to space. The crust became thicker and more stable. When the surface temperature finally fell below 100 Galactic, something transformative happened. The vapor accumulated in colossal quantities began to condense irreversibly. Dense clouds covered the planet and rain fell, not for hours or days, but for thousands of years. This incessant rain filled depressions, smoothed reliefs, dissolved minerals, created shallow seas, and eventually, global oceans. This birth of Earth as a blue planet was anything but smooth. The impacts that brought water also caused destruction, melting parts of the crust, generating magma tsunamis, and redesigning the surface countless times. The planet constantly remodeled itself while accumulating water. And even after the first oceans formed, bombardment continued, evaporating part of them, reaccumulating vapor, and restarting extreme climate cycles. What makes this story special is the improbable balance of factors. Earth was at the right distance to retain liquid water, but close enough to maintain internal heat and geological recycling. It received enough wet asteroids to form oceans, but not so many as to completely destroy the crust repeatedly. It had enough mass to hold its atmosphere, but not so much as to become a gas giant. Each of these variables could have turned out differently, and a small deviation would have given us a dry world like Mars or a hellish one like Venus. When Earth finally stabilized with permanent oceans, a dense atmosphere, and a still hot interior, it seemed the stage was set for life. But before anything complex could happen, the planet would still go through one final trauma. The collision with Theia, which would destroy the surface again, mix the entire interior, and give us, as a bonus, the moon. Nevas, Theia's sacrifice, the formation of the moon, and Earth's fine-tuning. When Earth seemed to have finally achieved a certain degree of stability, with its mass consolidated and its oceans forming, one last actor entered the scene to change everything. That actor was an entire planet. Theia. To understand the impact that gave us the moon, we need to start with Theia's origin and the orbital arrangement that made the collision practically inevitable. Theia probably formed in the same general region as Earth's orbit, within the solar system's inner zone. Like the other embryos, it began as a cluster of planetesimals, grew, differentiated internally, core, mantle, crust, and eventually reached a size comparable to Mars with something like 10% of Earth's mass. Theia's likely initial position was one of the gravitational stability points, called Lagrange points, located approximately 60 degrees ahead of or behind Earth in its orbit. While Theia remained small, this arrangement was relatively stable. But as it grew, gravitationally interacting with other bodies, small perturbations began to throw it off balance. The Lagrange point ceased to be a safe harbor. Over millions of years, Theia oscillated increasingly around the stable positions until its orbit distorted enough to cross Earth's. The collision on cosmic timescales ceased to be a distant possibility and became an almost certain consequence. The impact itself was something very different from anything we can imagine in human experience. Theia approached Earth at an estimated speed of about 15 km/s. This means that at the moment of collision, the energy released was comparable to trillions of nuclear bombs. But the most important detail was the angle, around 45 degrees. This oblique angle is the key to explaining both the destruction and the survival. When Theia struck Earth, the surface behaved like a liquid. The crust and mantle instantly fluidified under the impact's energy. Large portions of both bodies' mantles were torn off, vaporized, and launched into space. Theia's iron core, however, didn't fly off. Being denser, it plunged into Earth's interior like a projectile through gelatin, merging with our metallic core. This process explains why Earth's core is large and iron-rich. It is, in part, another planet's core. The immediate consequence of the impact was to transform Earth into a kind of synestia, a torus-shaped donut structure made of vaporized rock rapidly spinning around a central core. In orbit, a debris disk was established, composed mainly of material from Earth's and Theia's mantles, not their cores. This is why the Moon's composition, in terms of rocks, is so similar to Earth's mantle, but poor in metallic iron. Within this debris disk, gravity began to cluster the material. Unlike the slow formation of planetesimals at the system's beginning, here everything was already concentrated near Earth, with high density. Simulations suggest that the agglomeration that gave rise to the Moon may have taken very little time. Perhaps thousands of years, perhaps much less. The Moon was born hot, partially molten, and underwent its own internal differentiation, forming a small core and a silicate mantle. But the impact's effect was not just creating a satellite. It also redefined Earth's physical state. The planet's rotation was profoundly altered. Before the impact, Earth's day was probably only 6 to 8 hours. After swallowing Theia and redistributing mass, rotation was still fast, but over time it began to slow due to gravitational interaction with the nascent Moon. This interaction is what generates tides. Tides are more than a beach detail. They are a constant exchange of energy between Earth's rotation and the Moon's orbit. The Moon pulls the oceans, creating bulges. Earth, spinning faster than the Moon orbits, drags these bulges slightly forward. This lag creates a torque that transfers angular momentum from Earth's rotation to the Moon's orbit. Result: Earth slows down, days get longer, and the Moon slowly recedes, about 3.8 centimeters per year today. This process had two vital effects on habitability. First, it lengthened the day to friendlier durations, allowing smoother thermal cycles between day and night. Second, and more importantly, it stabilized Earth's axial tilt. Without the Moon, the tilt could vary chaotically over millions of years, oscillating between nearly 0 degrees and extreme values. This would cause violent and unpredictable climate changes, with ice ages and heat alternating on scales too rapid for complex life to adapt. With the Moon as an anchor, the tilt remains oscillating gently around 23.55 degrees. This gives us predictable seasons and relatively stable climate over long periods. In evolutionary terms, this is like providing a planet with a reliable environment in which ecosystems can arise, spread, and specialize without being reset all the time by extreme changes in insolation. Additionally, the impact with Theia may also have helped reset Earth's surface chemistry itself. By melting much of the crust and outer mantle, it allowed material from the depths to rise, releasing new gases, reorganizing primitive ocean's composition, and perhaps directly influencing the type of prebiotic chemistry that could occur later. Without this violent sacrifice, Earth probably wouldn't have the same rotation, the same axial stability, nor the same climate history. From the planetary formation perspective, the Earth we know, habitable, stable, with a large moon, is literally a fusion of two worlds. While Mercury was mutilated, Venus cooked, and Earth received its baptism of fire and water, Mars, in the next orbit, followed a path that seemed promising. Located about 228 million kilometers from the Sun, Mars was born in a transition region, still within the rocky zone of the ice line, but with occasional access to wetter materials from the asteroid belt. Its accretion began similarly to its inner siblings, silicate and iron dust clumping into planetesimals, which collided to form planetary embryos. During its first millions of years, Mars grew rapidly, reaching considerable size, perhaps 50% larger than we see today. Formation models suggest that Proto-Mars could have become a super-Earth, with mass comparable to Earth's or even greater. There was enough material in the region, rocks, metals, and traces of ice brought by orbital perturbations. Its iron core differentiated, the mantle formed, and evidence of ancient volcanoes, like Olympus Mons, the solar system's largest, indicates it was geologically active, expelling gases to create a dense atmosphere of CO2 x gas 2CO2 and nitrogen. Dry channels and fossil deltas on the surface suggest rivers and lakes in the past. Mars wasn't a weakling from the cradle. It had everything to rival Earth. So why did it stop growing? The answer lies in orbital geography and the arrival of an invader. Mars orbited in a supply zone between Earth and the main asteroid belt. There, the protoplanetary disk still had rocky debris to be swept up. But the problem was traffic. Its orbit crossed with remnants from Earth's formation and with the outer belt. In theory, this should have fed it. In practice, it made it vulnerable. The fatal blow came from Jupiter. During the Oligarchic phase, while the inner planets cannibalized each other, Jupiter, the gas giant, didn't stand still. It executed what astronomers call the grand tack, a radical orbital migration. Jupiter initially formed closer to the Sun, beyond the ice line, swallowing ice and gas. But interactions with the gas disk created drag, causing it to spiral inward toward Mars's orbit. Like a gravitational tractor, Jupiter cleared the path ahead of it. This invasion had three devastating effects on Mars. First, Jupiter swept up planetesimals and embryos orbiting in the Martian region, stealing the red planet's lunch. Second, its gravity perturbed the remaining orbits, accelerating destructive collisions among the leftover debris. Instead of merging with Mars, they fragmented. Third, when Jupiter reversed its migration, pulled by Saturn, it left behind an agitated asteroid belt which continued to bombard Mars without adding net mass. The result was a starving planet. Mars ended its main accretion with only 10% of Earth's mass and a core too small, about 20% of its volume versus 50% on Earth. Without a core large and hot enough to sustain a convective dynamo, Mars lost its primitive magnetic field about 4 billion years ago. Without this shield, the solar wind eroded its atmosphere over billions of years, drying oceans and transforming it into a frozen desert. Today, Mars is a relic. Ancient craters show a violent past. Extinct volcanoes reveal a cold interior, and polar glaciers remember what could have been. It is the survivor who lost the resource war. Its interrupted destiny creates the perfect hook for the next act. Jupiter wasn't just Mars's thief. It almost destroyed the entire inner system. The story's true villain now enters the scene. When we finish Block 2, it seems the inner system was almost ready. 4 rocky planets at different stages of evolution. Oceans beginning to form on Earth. Mars falling behind. Venus on the brink of climate collapse. But this sense of stability is illusory. In the middle of this scenario, a character who until then seemed distant decides to break the rules. Jupiter. Jupiter wasn't born where it is today. It formed a bit beyond the ice line, in a region rich in ice and gas. There, a rocky core of about 10 Earth masses grew very quickly until it had enough gravity to capture enormous amounts of hydrogen and helium from the protoplanetary disk. In a short geological time, Jupiter ceased to be just another embryo and became the largest object after the Sun, accumulating more than 300 times Earth's mass. When this happens, its relationship with the gas disk changes completely. A planet so massive doesn't just navigate in the disk. It deforms it. Jupiter's gravity excavates a gap in the gas, creating a kind of valley along its orbit. This gap, however, is not static. gas from the disk flows in and out, exerting drag forces on the planet. These interactions cause something counterintuitive. Instead of staying stationary, Jupiter begins to migrate. It literally spirals inward, toward the Sun. This inward movement is what we call the grand tack, a reference to a sailboat's maneuvering when changing direction. As Jupiter migrates toward the system's interior, it crosses the region where the asteroid belt and Mars's orbit are today. And it's here that the thread connecting to Block 2 becomes evident. Mars's diet is cut off. All solid material that could feed Mars's growth is swept away, dispersed or captured by Jupiter's gravity. Planetesimals and embryos that previously orbited peacefully are attracted, ejected, or thrown into eccentric orbits. It's as if a truck passed at high speed through a construction site, scattering the bricks everywhere. This invasion by Jupiter explains why Mars remained so small. While Earth and Venus had access to sufficient raw material to grow, Mars was formed and abandoned too early in a region that was emptied by the migrating giant. Its growth was literally interrupted by the invader's passage. What seemed like an isolated failure in Mars's formation is now understood as a side effect of a larger process, the movement of the gas giants. But the grand tack story doesn't end with Jupiter falling into the Sun. If that had happened, the entire inner system would have been destroyed, including us. What stops it from continuing this suicidal trajectory is the entrance of another giant in formation, Saturn. When Saturn reaches significant mass, it also interacts with the gas disk. At a certain moment, the two giants enter gravitational resonance, a kind of orbital synchronization. This resonance changes the direction of the disk forces on them. Instead of continuing to spiral inward, Jupiter and Saturn begin to migrate outward, like a pair of skaters pulling each other away from the center. It's at this point that the grand tack completes its maneuver. Jupiter breaks its invasion and retreats to the approximate orbit where it is today. But the damage was already done. It had already perturbed the inner belt, stolen Mars's potential mass, and redistributed debris throughout the system. The middle of the track was marked by this trail of gravitational destruction, which brings us to the next topic. The debris graveyard that remained from this passage. When we hear about the asteroid belt, it's common to imagine a planet that exploded or was destroyed by some catastrophic event. This idea is cinematic, but it doesn't match what physics shows us. The asteroid belt, located between Mars and Jupiter, is not the corpse of a destroyed planet. It's a planet that never got to be born. And the main culprit for this is, again, Jupiter. Before the giant's migration, the region between 2 and 4 astronomical units from the Sun was just another stretch of the debris disk. There was enough solid material there to form one or more planets with mass similar to Earth's. Planetesimals and rocky embryos were following the same script as the others, colliding, growing, differentiating. In a system without Jupiter, this region would probably have produced 1 or 2 respectable planets. However, Jupiter's gravitational weight completely alters this trajectory. As Jupiter migrates inward, it crosses the outer part of this region. Its powerful gravity acts as an agitator. Instead of allowing small bodies to meet at low speeds, which favor merging, it increases the relative velocity between them. Collisions that could build larger bodies become destructive impacts that fragment what had already been built. At the same time, many of these pieces are ejected into eccentric orbits or even expelled from the solar system. When Jupiter makes the return maneuver outward with Saturn, the situation doesn't improve for the survivors of that sector. Now the region between Mars and Jupiter becomes a doubly perturbed gravity field. Jupiter's permanent presence nearby prevents asteroids from finding enough stability to cluster. Each time a body in this band grows a bit larger, it becomes more sensitive to Jupiter's perturbations and has its orbit altered, increasing the risk of destructive collisions or being thrown outward. This creates a strange equilibrium. Asteroids are too large to simply dissolve, but too small to unite into something bigger. The result is a population of millions of bodies, ranging in size from grains to hundreds of kilometers, spinning in relatively stable orbits, yet frozen in their incomplete state. They are literally leftover construction materials that were never used. Each one preserves in its composition the chemistry of the original nebula, making them invaluable time capsules. The belt also became divided into families. Near the inner part, closer to Mars, we find rocky and metallic asteroids, similar to those that formed the inner planets. Further out, on the edge with Jupiter's orbit, appear darker asteroids rich in carbon and water, the carbonaceous asteroids. These latter, as we've seen, were fundamental in bringing water to Earth. In other words, the asteroid belt is not just a graveyard, it's also a stockpile of materials that directly influenced our planet's evolution. Orbital resonances with Jupiter, points where an asteroid's orbital period relates in a simple way to Jupiter's, such as 3:1 or 2:1, create forbidden zones within the belt, known as Kirkwood gaps. In these regions, any body that establishes itself is quickly dislodged, reinforcing the belt's fragmented and incomplete structure. It is a place where Jupiter's gravity acts as a merciless caretaker. Any attempt at organization into something larger is undone over time. When we look at the belt as a whole, it's clear how it fits into the story's thread. The same movement by Jupiter that stole Mars's mass and nearly compromised the inner system's development also condemned this band to be a debris graveyard. It's a frontier. Inside, the realm of surviving rocky planets. Outside, the domains of the gas giants. And right there, in the middle, the remains of the interrupted work that silently tell everything the giant did when crossing the system's heart. While Jupiter plunged toward the sun like an uncontrolled gravitational tractor, the inner system's fate hung by a thread. If it had continued its inward migration, it would have reached Mars's current orbit and eventually penetrated even deeper. In this catastrophic scenario, Earth and Venus would have been bombarded by ejected debris, their orbits would have been destabilized, and the window for life as we know it might never have opened. But something braked Jupiter midway. That something was Saturn. Saturn formed a bit later than Jupiter, also beyond the ice line, but a bit farther out. Like its bigger brother, Saturn began as a core of rock and ice that, upon reaching about 10 Earth masses, initiated the gas capture process. However, Saturn arrived late to the party. When it began swallowing hydrogen and helium from the disk, Jupiter had already swept up much of the region's gas, leaving less material available. That's why Saturn ended up with about 1/3 of Jupiter's mass, becoming lighter and less dense. A difference we see even today in its internal structure and famous rings. But it was precisely this mass difference and formation timing that allowed Saturn to play the role of savior. As Saturn grew and interacted with the gas disk, it also began to migrate, and here enters a crucial concept of orbital dynamics. Orbital resonance. Resonance happens when two bodies have orbital periods that relate by simple ratios, like 2.1 or 3.2. When Jupiter and Saturn entered resonance, probably 3.2 or 2.1, their gravitational influences on the gas disk began to add up constructively. This synchronization completely changed the forces the disk exerted on them. Before, Jupiter felt drag that pushed it inward. Now, with Saturn pulling from outside and the disk redistributing gravitational torque, the forces reversed. The pair of giants began to migrate outward, moving away from the sun. It's as if Saturn had grabbed Jupiter by an invisible gravitational rope and pulled it back to safer regions. The cosmic emergency brake was engaged. This return movement, part of the grand tack, literally saved the inner system. Jupiter retreated to approximately 5.2 astronomical units from the Sun, where it remains today. Saturn stabilized around 9.5 AU. With the giants now positioned farther out, gravitational pressure on the rocky planets decreased. Mars, although already mutilated, could at least remain in its orbit. Earth and Venus continued their trajectories without being swept away or shattered. The asteroid belt, though condemned to eternal fragmentation, found a stable orbital configuration. But stabilization didn't mean immediate peace. The giants' outward movement had violent and lasting side effects. As they retreated, Jupiter and Saturn perturbed objects that were beyond their orbits, in what we today call the Kuiper belt, and even more distant regions. These icy bodies were launched into chaotic orbits. Millions of them were ejected into interstellar space. Many others were hurled inward toward the inner system, and it was this rebound effect that triggered one of the most striking events in planetary history: the Late Heavy Bombardment. If you observe the moon on a clear night, you'll see its surface marked by dark spots and bright areas. These spots, the so-called lunar Maria, are not water oceans, but gigantic basins of solidified lava. They were created by colossal impacts that penetrated the lunar crust and released magma from the mantle below. What's impressive is that these craters don't date from the moon's formation 4.5 billion years ago. They are between 4.1 and 3.8 billion years old. This means that about 500 million years after the solar system seemed to have stabilized, something triggered a renewed wave of violence. This event is known as the Late Heavy Bombardment, or LHB. The cause of this late bombardment is directly linked to the giants' migration we just described. When Jupiter and Saturn retreated to their current orbits, they crossed regions populated by icy and rocky planetesimals. These objects, which had orbited peacefully for millions of years, were suddenly caught in a gravitational whirlpool. Their orbits were stretched, twisted, and launched into eccentric trajectories. A significant fraction of these bodies was hurled into the inner system. Earth, which had already cooled its crust, formed primitive oceans, and perhaps even developed the first forms of primordial life, was bombarded again. Asteroids and comets tens of kilometers in diameter rained down on the surface. Each impact vaporized local oceans, created basins hundreds of kilometers wide, injected dust into the atmosphere, and sterilized vast regions. If there was life before the LHB, it may have been extinguished or forced to take refuge in the ocean depths, near hydrothermal vents. The moon, without an atmosphere or plate tectonics to erase the scars, preserved the record of this bombardment with crystalline clarity. The lunar impact basins like Mare Imbrium, Mare Serenitatis, and Mare Tranquillitatis are permanent witnesses to this era of renewed chaos. Lunar rock samples brought back by the Apollo missions confirm that most of the large craters formed in this narrow period between 4.1 and 3.8 billion years ago. Mars was also hit. Although smaller and with less gravity to attract projectiles, its surface shows gigantic craters from this period. Some of these basins may have been temporarily filled with water released from the subsurface by the heat of impacts, creating ephemeral lakes that lasted perhaps thousands of years before evaporating or freezing. Mercury and Venus, although harder to study, also showed geological signs consistent with intense bombardment at this time. Paradoxically, the late bombardment may have been both a destructive and creative event. The impacts brought not only destruction but also additional delivery of volatiles, water, organic compounds, and gases that may have replenished Earth after the loss of part of its primitive atmosphere. Some scientists suggest the LHB may even have seeded the necessary ingredients for life, bringing complex organic molecules from deep space. Around 3.8 billion years ago, the bombardment finally ceased. The stock of projectiles was exhausted. The giants stabilized their orbits. The solar system, for the first time in its history, entered a phase of relative calm. Craters stopped multiplying. Earth's oceans could settle down. Primitive life, if it survived the impacts or arose shortly after, finally found a stable stage to evolve. The trauma had passed, but the witnesses of this period still orbit, silently, in the asteroid belt. Amid the chaos that Jupiter caused in the asteroid belt, two bodies managed not only to survive, but also to preserve crucial information about the solar system's first days. These bodies are Ceres and Vesta, the belt's two largest objects. While trillions of smaller fragments were shattered, ejected, or pulverized, Ceres and Vesta remained large enough to maintain their structural integrity. They are literally time capsules. Unedited geological archives from the era of planetary formation. Vesta is the oldest intact planetary embryo we can study up close. With a diameter of about 525 kilometers, Vesta differentiated internally early in the solar system. This means that, like the rocky planets, it melted and separated its interior into layers: iron-nickel core, rock mantle, and basalt crust. This differentiation was driven by heat from radioactive decay of short-lived elements, like aluminum-26, which existed only in the system's first millions of years. What makes Vesta so valuable is that, unlike Earth, Mars, or Venus, it never had plate tectonics or atmospheric erosion to erase its history. Its surface preserves impact craters billions of years old. One of these craters, called Rhea Silvia, is 500 kilometers in diameter, nearly the size of the asteroid itself. The impact that created it was so violent that it ejected fragments of Vesta into space, many of which fell to Earth as meteorites. These meteorites, called AED, Howardite Eucrit Diogenite, are pieces of Vesta's crust and mantle. By studying them in the laboratory, we can literally dissect a protoplanet without needing to land on it. Ceres, on the other hand, tells a different story. With a diameter of about 940 kilometers, Ceres is the asteroid belt's largest object and was reclassified as a dwarf planet in 2006. Unlike Vesta, Ceres is not purely rocky. It formed in a region slightly farther from the Sun, where ice was stable. Its composition is a mixture of rock and water ice. It is essentially a hybrid between a rocky asteroid and a comet. NASA's Dawn spacecraft orbited Ceres between 2015 and 2018 and made surprising discoveries. Bright spots on the surface revealed salt deposits, evidence that Ceres had, and perhaps still has, an ocean of salty liquid water below its crust. This places Ceres in the same category as ocean worlds like Europa, Jupiter's moon, and Enceladus, Saturn's moon, though on a much smaller scale. The presence of organic compounds on the surface also raises questions about the prebiotic chemistry possible in small, icy bodies. Together, Ceres and Vesta represent two extremes of the belt. Vesta, the dry, rocky protoplanet that began to become a planet but was interrupted. Ceres, the icy hybrid that preserves the chemistry of the ice line. Both are survivors of a gravitational massacre. Each crater, each crack, each grain of dust on their surfaces tells the story of the violence Jupiter brought, but they also tell something more hopeful, that even amid chaos, structures can persist. Information can be preserved. And billions of years later, we, born from the dust of these same processes, can send probes to read these messages from the past. To understand why Jupiter and Saturn are so different from the rocky planets, we need to return to the concept of time. Planet formation is not an infinite process. It has a fatal deadline. And this deadline is dictated by the central star itself, the Sun. While the inner rocky planets had millions of years to grow, since rocks and metals are permanent solids, the gas giants faced a race against the clock. The gas from the protoplanetary disk, hydrogen and helium, which make up 99% of the available mass, wouldn't stay there forever. During the first millions of years, the young Sun was an unstable and violent star, going through the phase called T-Tauri. In this phase, the star is still adjusting its internal equilibrium between nuclear fusion and gravity. The result is intense magnetic activity, frequent eruptions, and most importantly, the emission of an extremely powerful stellar wind, orders of magnitude stronger than the current solar wind. This wind is composed of charged particles, protons, electrons, traveling at hundreds of kilometers per second. When this wind struck the protoplanetary disk, it began to blow the light gas, hydrogen and helium, out of the system. It's a photoevaporation process. The Sun's ultraviolet radiation heats the gas until it reaches escape velocity and simply evaporates into interstellar space. This process is fast on astronomical scales. Models indicate that between 3 and 10 million years after the Sun's ignition, practically all the primordial gas from the disk was dispersed. only solids remained: rocks, metals, and ice. For Jupiter and the other gas giants, this meant an extremely short operational window. If they wanted to become giants, they needed to capture the gas before it disappeared. But there's a problem. Gas doesn't stick by itself. Unlike rocks that collide and merge, gas easily escapes into space unless held by very strong gravity. And to generate strong gravity, you need mass. A lot of mass. More specifically, it was necessary to build a solid core of rock and ice with at least 10 Earth masses. This value is not arbitrary. It represents the theoretical threshold where a body's gravity becomes strong enough to begin efficiently capturing and retaining gas. Below this, gas simply escapes. Above this, the planet enters a regime called runaway gas accretion. So the race wasn't just grow fast, it was grow fast enough to reach critical mass before the gas disappeared. Jupiter won this race. And it won spectacularly. Jupiter's story begins in the region just beyond the ice line, where the disk's temperature dropped enough for water and other volatiles to solidify. This chemical difference was decisive. While the inner planets had only rocks and metals, less than 1% of the disk's mass, Jupiter had access to rocks, metals, and ice, especially water ice, which is incredibly abundant in the universe. This tripled or quadrupled the amount of solid material available. Accretion began the same way as in the rocky planets. Dust becoming pebbles, pebbles becoming planetesimals, planetesimals becoming embryos. But in Jupiter's region, this process was supercharged by the abundance of ice. Proto-Jupiter grew fast, swallowing everything around it. In perhaps 1 to 2 million years, a fraction of the time it took to form Earth, Jupiter's core reached critical mass: 10 Earth masses. When this happened, the physics changed completely. With 10 Earth masses, the core's gravity became strong enough to begin pulling the surrounding gas from the disk. Initially, this process was slow and controlled. Gas fell onto the planet, heated due to gravitational compression, and part of it escaped again. It was a delicate balance between capture and loss. But as more gas was captured, Jupiter's total mass increased, and more mass means more gravity. More gravity means more efficient gas capture, and this, in turn, increases the mass even more. It's a positive feedback cycle known as runaway accretion. In practical terms, it means that once the threshold is crossed, growth becomes exponential. Jupiter began swallowing gas at a dizzying rate. Models suggest that at the peak of accretion, Jupiter may have been accumulating the equivalent of several Earth masses per century. On human scales, this seems slow. On planetary scales, it's an avalanche. The process continued until Jupiter reached about 318 Earth masses, its current mass. At this point, two factors stopped the growth. First, as we saw, the solar wind began to disperse the disk's remaining gas. Second, Jupiter's own presence began to alter the disk's structure around it, creating what we call a gap, a gravitational trench that isolates the planet from the rest of the gas. This second phenomenon deserves special attention, because it explains not only Jupiter's final size, but also how it became the solitary king of the outer system. As Jupiter fattened, its growing mass began to interact increasingly strongly with the surrounding gas disk. A massive planet orbiting within a disk is not a passive body. It disturbs the material around it, creating density waves, similar to the waves a boat creates as it moves through water. In Jupiter's case, these waves were so strong that they began to excavate a deep valley in the disk, the gap. The physics behind the gap is fascinating. Jupiter exerts gravitational forces, called torques, on the gas orbiting closer to the Sun and on the gas orbiting farther out. These forces tend to push gas inward and outward, moving it away from the planet's orbit. Imagine Jupiter as a large rock rolling down a dirt road. It pushes the dirt to the sides, creating a clean strip along the path. The same happens in the disk. Gas is displaced from Jupiter's immediate vicinity, creating an almost empty, forbidden zone around its orbit. The width of this gap depends on the planet's mass and the disk gas's viscosity. For Jupiter, The gap extended several astronomical units, creating a kind of cosmic trench. This had two important consequences. First, it isolated Jupiter from the main gas reservoir. With less gas available nearby, the accretion rate slowed dramatically. Jupiter could still capture gas that leaked through the gap due to disk turbulence, but the initial explosive growth was braked. This explains why Jupiter stopped growing when it did. It literally consumed all the gas within its reach and isolated itself from the rest. Second consequence, the gap divided the disk into two distinct regions, one inner and one outer. This division had profound implications for the formation of other planets. Saturn, which was forming in the outer region, had access to a separate gas reserve. The inner rocky planets, which had already finished their solid accretion, were definitively isolated from the outer gas. Jupiter's gap functioned as a gravitational wall, separating the inner domains, rocky and dry, from the outer domains, giant and gaseous. Modern observations of protoplanetary disks around other stars confirm that gaps like this are common. Telescopes like ALMA, Atacama Large Millimeter Array, have detected dozens of disks with concentric rings and dark gaps, indicating the presence of forming giant planets. These images are essentially photographs of baby solar systems going through the same phase our system went through 4.5 billion years ago. Jupiter, viewed from outside at that time, would have appeared as a dark shadow in a bright ring of gas. The gap's creation also had an unexpected effect. It helped stabilize Jupiter's orbit. Before the gap, Jupiter was subject to strong torques from the disk that caused it to migrate, as we saw in the Grand Tack. But once the gap was fully opened, the disk could no longer exert efficient torques on it. Jupiter locked its position. It became in effect a solitary king, massive, isolated, and gravitationally dominant, reigning over an empty region it carved itself. And it was from this isolated throne that it governed the fate of the entire solar system, pushing Saturn outward, perturbing the asteroid belt, and shaping the orbits of the ice giants that would follow. When we look at Jupiter today, we see not just a planet, but a planetary system in miniature. It has 95 known moons, but 4 stand out: Io, Europa, Ganymede, and Callisto, the so-called Galilean moons discovered by Galileo Galilei in 1610. These 4 moons are not captured asteroids. They were born along with Jupiter, in a way surprisingly similar to how planets were born around the Sun. To understand this, we need to return to the moment when Jupiter was swallowing gas uncontrollably. During the runaway accretion phase, Jupiter didn't just capture gas directly, it also created a circumplanetary disk around itself. When gas from the solar protoplanetary disk fell toward Jupiter, it couldn't simply fall in a straight line. Due to conservation of angular momentum, the same physics that flattened the solar nebula, the gas began to orbit Jupiter, forming a disk on a smaller scale, a miniature version of the disk that existed around the Sun. This circumplanetary disk had all the characteristics of the solar disk. It was hot at the center, near Jupiter, cold at the edges, and full of dust and ice mixed with gas. And exactly as in the solar disk, dust and ice began to collide, stick together, and form larger bodies. These bodies grew until they became the moons we see today. The formation sequence was practically identical. Grains became pebbles, pebbles became lunar planetesimals, and these bodies merged to create the 4 large moons. What makes this process fascinating is that Jupiter's circumplanetary disk also had an internal ice line. Near Jupiter, where the heat from the planet's accretion was intense, only rocky and metallic materials could survive. Farther out, where cold dominated, ice was abundant. This explains the composition of the Galilean moons. Io, the innermost, is almost entirely rocky, made of silicates and metals with practically no ice. Europa has an ice crust, but is still mostly rocky. Ganymede and Callisto, the most distant, are approximately half rock and half ice. It's a perfect chemical progression, mirroring the division between the inner rocky planets and the outer ice-rich ones. But Jupiter didn't become a star, despite having enough mass to form its own solar system. Venus To initiate nuclear fusion of hydrogen and become a true star, Jupiter would need about 80 times more mass, approximately 80 Jupiters or 0.08 solar masses. It is technically a failed star, or more correctly, a gas giant that never had enough mass to turn on the nuclear furnace. Still, it emits more energy than it receives from the Sun. This happens because Jupiter is still slowly contracting due to gravity, and this compression releases heat, a process called Kelvin-Helmholtz contraction. This internal heat fuels Io's extreme volcanic activity and maintains liquid oceans beneath the icy crusts of Europa and Ganymede. The Galilean moons, therefore, are not just satellites. They are miniature planets, formed by processes that mirror planet formation around the Sun. Io is geologically active with hundreds of volcanoes. Europa possesses a global ocean of salty liquid water beneath its ice crust, one of the most promising places to search for life in the solar system. Ganymede is the solar system's largest moon, larger even than Mercury, and has its own magnetic field. Callisto is a fossil record covered with ancient craters that were never erased. Jupiter is not just a planet. It is the king of a kingdom, and its moons are the worlds that orbit its throne. While Jupiter dominated the outer system's inner region, a bit farther out, another giant began to form, Saturn. But Saturn arrived late. When its core reached the 10 Earth masses needed to initiate gas capture, Jupiter had already consumed a significant portion of the available gas reservoir. Additionally, time was running out. The young solar wind was already dispersing the disk's remaining gas. Saturn managed to capture enough hydrogen and helium to become a giant, but ended up with only 1/3 of Jupiter's mass, about 95 Earth masses. This mass difference had profound consequences on Saturn's internal structure. Jupiter is so massive that its own gravity compresses the hydrogen in its interior to very high densities, making it dense, 1.33 g/3, slightly denser than water. Saturn, with less mass, cannot compress its hydrogen as efficiently. The result is that Saturn is surprisingly fluffy. Its average density is only 0.687 g/3, less dense than water. If there were an ocean large enough, Saturn would float in it. It is the solar system's lightest giant planet, a golden yellow gas balloon wrapped in layers of ammonia and methane clouds. But Saturn's most iconic characteristic is not its size or density. It's its rings. They are so spectacular that they overshadow any other structure in the solar system. They extend for hundreds of thousands of kilometers, but are only a few dozen meters thick, proportionally thinner than a sheet of paper. Composed almost entirely of water ice, with traces of rock, Saturn's rings shine brightly under sunlight, creating the image that defines the planet. For a long time, it was believed that the rings were as old as Saturn, remnants of the circumplanetary disk that formed its moons. But recent data from the Cassini mission, which orbited Saturn between 2004 and 2017, revealed something surprising. The rings are young, very young. They are probably between 100 and 400 million years old, which in cosmic terms is practically yesterday. To put it in perspective, dinosaurs were already walking on Earth when Saturn's rings formed. This completely changed the narrative. The rings are not a fossil from planetary formation. They are the result of a recent catastrophe. The most accepted theory is that a medium-sized moon, perhaps the size of Mimas, about 400 kilometers in diameter, orbited Saturn in a stable orbit. But something disturbed this stability. Perhaps a gravitational interaction with another moon, perhaps a collision with a wandering comet. The moon's orbit began to decay, bringing it closer and closer to Saturn until it crossed the so-called Roche limit. The Roche limit is the minimum distance a body can orbit a planet without being torn apart by tidal forces. Within this zone, the difference in gravitational attraction between the body's near side and far side becomes greater than the force holding the body together. The moon was literally torn apart by Saturn's gravity. Its rocky core fell into the planet, but its ice crust, Billions of tons of frozen water remained in orbit, spreading along Saturn's equatorial plane. These ice fragments collided with each other, broke into increasingly smaller pieces, and eventually formed the rings we see today. Each particle in the rings, from sand-sized grains to house-sized blocks, is a piece of this destroyed moon orbiting eternally around the planet that killed it. The rings are not permanent. They are slowly raining onto Saturn as particles lose energy and spiral inward. In about 100 million years, the rings may disappear completely. Saturn, then, is the planet that arrived late to the gas race, became lighter and less dense than its brother Jupiter, but gained, for a brief moment in cosmic history, the most spectacular visual crown in the entire solar system. Its rings are, at the same time, a reminder of the orbital violence that still persists, and a symbol of the beauty that can be born from destruction. Jupiter may be the king of mass, but Saturn is, without doubt, the lord of appearance. When we look at Uranus and Neptune, orbiting at 19 and 30 astronomical units from the Sun respectively, we face a baffling problem. These two planets shouldn't exist. Not in the positions where they are, not with the masses they have, and definitely not in the time they had available to form. This is the time paradox, one of the greatest mysteries of planetary formation, which was only solved when astronomers accepted a strange truth. Uranus and Neptune are immigrants. They weren't born where they are today. To understand the paradox, we need to revisit the physics of planetary accretion. As we saw in previous blocks, planets grow through collision and fusion of planetesimals. The rate of this growth depends directly on three factors: the density of available solid material, the orbital velocity of planetesimals, and the mass of the growing core. In the orbits where Uranus and Neptune are today, all these factors conspire against planetary formation. First, material density in the outer solar system region is extremely low. The protoplanetary disk's mass decreases drastically with distance from the Sun. While Earth's region had perhaps 10 Earth masses of solids concentrated in a few million kilometers, the Uranus and Neptune region had only fractions of an Earth mass scattered across billions of kilometers. There simply weren't enough bricks close enough together to build a large planet. Second, orbital periods are absurdly long out there. Neptune takes 165 Earth years to complete a single orbit around the Sun. This means encounters between planetesimals were rare. If two bodies only cross paths every century or more, the collision and fusion process becomes glacially slow. In the inner regions, where years lasted months, planetesimals collided constantly, accelerating growth. Out there, collision frequency was hundreds of times lower. Third, available time was limited. As we saw in Block 4, disk gas was dispersed by the solar wind in about 3 to 10 million years. Even though Uranus and Neptune didn't need to capture as much gas as Jupiter or Saturn, they still needed to form solid cores large enough to retain their hydrogen and helium atmospheres. But calculations show that, at the density and collision rate of their current orbits, forming a 10 to 15 Earth mass core would take between 100 million and 1 billion years, at least 10 times longer than gas was available. This creates a logical impossibility. Uranus and Neptune exist. They have 14.5 and 17 Earth masses respectively, with solid cores and thick hydrogen and helium envelopes. But according to the laws of physics applied to their current orbits, they shouldn't have had time to form. This paradox tormented astronomers for decades. The only possible solution was radical. They didn't form where they are today. They formed much closer to the Sun, where material density was higher and orbital periods were shorter. And then something pushed them outward. That something was again Jupiter and Saturn. And the story of this expulsion is told by a revolutionary model called the Nice model, named after the French city where it was developed in 2005. This model not only solves the Uranus and Neptune paradox, but also explains the late heavy bombardment, the Kuiper belt structure, and the Oort cloud's existence. It's the final piece of the solar system formation puzzle. The solar system's initial configuration, soon after the four giants' formation, was very different from what we see today. Jupiter, Saturn, Uranus, and Neptune were all more compact, orbiting in a region between 5 and 15 astronomical units from the Sun. Uranus and Neptune were probably between Jupiter and Saturn, or just beyond Saturn, in nearly circular orbits. The system seemed stable, but it was a fragile stability, sustained by a delicate gravitational balance. Beyond the giants' orbits extended a vast disk of icy planetesimals, the leftovers from planetary construction, composed mainly of water ice, methane, and ammonia. This disk was dense and massive, containing perhaps 50 Earth masses of material. For hundreds of millions of years, this disk remained relatively untouched, but the giant planets exerted small gravitational tugs on it, and slowly these tugs began to change the planetesimal's orbits. Some of these icy bodies were deflected into orbits that crossed with the giants. When a planetesimal passes near a planet, an orbital energy exchange occurs. If the planetesimal passes behind the planet, in the direction opposite to orbital motion, it gains energy and is accelerated, being launched into more distant orbits or even ejected from the solar system. If it passes in front, it loses energy and falls toward the Sun. But through momentum conservation, the planet suffers the opposite effect. It also loses or gains orbital energy. Here's the key to the nice model. Jupiter, being much more massive, ejected planetesimals outward very efficiently. In doing so, it lost orbital energy and migrated slightly inward, toward the Sun. Saturn, Uranus, and Neptune, on the other hand, interacted with planetesimals that Jupiter had perturbed. By scattering these bodies, they gained orbital energy and migrated outward, moving away from the Sun. It was a slow but relentless dance. For hundreds of millions of years, this migration was gradual. But then, something dramatic happened. Jupiter and Saturn crossed an orbital resonance, probably the 2.1 resonance, where Jupiter completed exactly 2 orbits for each Saturn orbit. When two massive bodies enter resonance, their gravitational influences amplify each other. The result was a sudden and violent destabilization of the entire outer system. The orbits of all 4 giants became chaotic. Uranus and Neptune, which previously had nearly circular orbits, were launched into eccentric trajectories. They were hurled like stones in a gravitational sling, crossing the dense disk of icy planetesimals that lay beyond Saturn. This encounter was catastrophic for both sides. Planetesimals were scattered in all directions. Some fell into the inner system, causing the late heavy bombardment. Others were ejected into interstellar space, and others were pushed into distant orbits, forming the Kuiper belt and Oort cloud. Uranus and Neptune, as they crossed and dispersed this disk, lost orbital energy with each interaction. They decelerated and ended up trapped in more distant orbits, exactly where we see them today. Neptune, which probably started closer to the Sun than Uranus, may have overtaken Uranus during this chaotic migration, switching places with it. This would explain why Neptune is slightly more massive than Uranus. Despite being farther out, it had access to more material during the initial formation phase. The nice model also explains why the giants' orbits have small eccentricities and inclinations. They're not perfectly circular because they were perturbed during migration. It explains the Kuiper belt, which is abruptly truncated at about 50 AU, exactly where Neptune's gravitational influence during its migration would sweep objects. It explains Kuiper belt objects in resonance with Neptune, like Pluto, which were captured during migration. And it explains the timing of the late heavy bombardment. The resonant chaos happened about 600 million years after the system's formation, exactly when lunar evidence shows the bombardment occurred. Uranus and Neptune, therefore, are not natives of the icy darkness where they dwell. They are refugees, exiled to the solar system's periphery by forces they couldn't control. They were born near heat and light, where planetary construction was viable. But they were banished to the shadows by Jupiter's gravitational tyranny. And on this journey into exile, they reshaped the entire solar system, scattering the remnants of planetary construction from the inner system to the edges of space. They are not just planets. They are the agents of the last great act of violence in planetary formation history, and the scars of that act still mark every corner of our system. One of the NICE model's most intriguing predictions is that the order of the ice giant planets wasn't always what we see today. Computer simulations that best reproduce the solar system's current configuration suggest something surprising. Neptune was born closer to the Sun than Uranus. During the chaos of the Great Migration, they switched places. This cosmic overtaking not only explains their current positions, but also resolves several anomalies in their physical properties that would otherwise be inexplicable. Let's start with mass. Neptune has 17.1 Earth masses, while Uranus has 14.5. At first glance, this seems strange. If both formed through accretion of material from the protoplanetary disk, the planet closer to the Sun should have access to more material and therefore be more massive. But Uranus, which is closer, is the smaller of the two. This only makes sense if Neptune originally formed in an orbit interior to Uranus's, where disk density was slightly higher and it could grow more before migration began. The internal composition of the two planets also offers clues. Both are called ice giants, but this name is misleading. They're not made primarily of solid water ice. Their interiors are actually composed of a hot, dense mixture of water, methane, and ammonia in exotic states. Supercritical fluids under immense pressures that behave neither like liquids nor like gases. Wrapped around these icy mantles, hot but rich in volatile compounds, are rocky cores of silicates and metals. Above all this, thick atmospheres of hydrogen, helium, and methane. Neptune, however, has a significantly higher internal heat flow than Uranus. It radiates 6 times more energy than it receives from the Sun, indicating an active internal source, probably residual heat from formation still being slowly released through internal convection processes. Uranus, strangely, emits very little internal heat, almost in equilibrium with the solar energy it receives. This difference can be explained if Neptune went through a more turbulent migration, crossing denser regions of the planetesimal disk, heating its interior through impacts and gravitational friction during the outward journey. During the resonant instability phase, when Jupiter and Saturn destabilized the system, Uranus and Neptune were launched into eccentric orbits that made them plunge into the dense disk of icy planetesimals beyond Saturn. But they didn't follow identical trajectories. Neptune, initially closer and with a slightly different orbit, interacted more intensely with the disk. It crossed denser regions, scattering more objects and, in doing so, losing more orbital energy. This energy loss braked it and threw it into a more distant orbit than Uranus's. Uranus, on the other hand, may have had a slightly less chaotic trajectory, interacting less intensely with the disk. Or in some simulation scenarios, it may have been deflected by a close encounter with Saturn, or even with Neptune, being pushed into a more interior orbit during the swap. The final result was a position reversal. The planet that was born as the third giant, Neptune, ended up as the fourth, and vice versa. This swap has observable consequences. The Kuiper belt, for example, shows clear signs of Neptune's migration. Objects like Pluto are trapped in a 3.2 resonance with Neptune. They complete 2 orbits for every 3 of Neptune's. This resonance is no coincidence. It was established during Neptune's outward migration. As Neptune slowly moved away, it swept objects ahead of it, capturing some in stable resonances. If Neptune had always been where it is today, these resonances wouldn't have formed this way. They are literally gravitational footprints left by the giant's passage. There's also dynamical evidence. Simulations show that if you run the movie backward and reverse the planet's current orbits, allowing orbital physics to undo the migration, Neptune and Uranus converge to inverted positions. Neptune more internal, Uranus more external. When you run the movie forward again, allowing the resonant instability, they switch places in most scenarios, ending in the configuration we see today. The identity swap between Uranus and Neptune is therefore a direct consequence of the Great Migration's violence. It wasn't a gentle or predictable process. It was chaotic, dependent on sensitive initial conditions and complex gravitational interactions among four giants and trillions of planetesimals. The fact that we've managed to reconstruct this history through simulations, observations of orbital resonances, and analysis of physical properties is an impressive victory for modern astrophysics. And this story isn't over yet, because one of the protagonists, Uranus, bears a deep and permanent scar from this era of chaos. It was literally knocked on its side. When pushed to the outer regions, Uranus and Neptune entered a physico-chemical regime completely different from the inner planets. Sunlight reaching Neptune is about 900 times weaker than what reaches Earth. Temperatures in the upper clouds are near 200 degrees C. At this distance, almost all the heat that matters doesn't come from the sun, but from inside the planet itself. It's in this environment that chemistry changes behavior and exotic phenomena take center stage, like the famous diamond rain. Both Uranus and Neptune are composed mostly of three simple elements: hydrogen, helium, and carbon, the latter mainly in the form of methane, CH4 4CH4. Under pressure and temperature conditions in their upper layers, methane remains as gas. It's what gives both planets their blue-green coloration, absorbing red light and reflecting blue. But as we descend into the interior, pressure increases rapidly and temperature rises. At sufficiently great depths, the combination of high pressure and heat begins to chemically break down methane. When methane dissociates, carbon atoms are released from hydrogen. At pressures of hundreds of thousands to millions of atmospheres, these carbon atoms don't behave as they do on Earth's surface. They can cluster into ultra-stable crystalline structures, diamonds. Laboratory simulations and theoretical models suggest that inside Uranus and Neptune, these diamonds form solid hail that literally falls toward the planet's depths, a diamond rain. As they descend, these solid drops of crystalline carbon can melt in deeper layers, forming oceans of liquid carbon or even a kind of diamond sludge. This extreme chemistry doesn't stop there. The mixture of water, ammonia, and methane under titanic pressures enters a state called supercritical. Instead of having clear separations between solid, liquid, and gas, substances come to exist in a single phase, dense, highly conductive, and exotic. In Neptune, much of the interior may be an immense supercritical ocean, neither water, nor ice, nor vapor in the common sense, but something intermediate with properties of all. This ocean is probably responsible for the electrical conduction that generates the planet's magnetic field. Speaking of magnetic fields, both Uranus and Neptune exhibit intense but extremely strange fields, offset from the planet's center and strongly tilted relative to the rotation axis. This indicates that the dynamo generating them is not in a spherical metallic core like Earth's, but in upper layers, possibly in this supercritical ocean region. Instead of a spinning, convecting iron core, we have layers of ionic and supercritical fluids moving under colossal pressures, creating complex and asymmetric magnetic patterns. Adapting to the cold for Uranus and Neptune meant becoming internal thermal machines. Even receiving little energy from the sun, Neptune in particular still releases considerable internal heat, more energy to space than it receives. This residual heat from formation and perhaps from internal processes, like sedimentation of heavier materials or release of gravitational energy from diamond rain, generates convection and extremely powerful winds. On Neptune, we've already measured winds of over 2,000 km/h, some of the fastest in the solar system, on a planet where light barely arrives. All this makes the ice giants natural laboratories of extreme physics. They show how planetary formation is not just a question of where and when, but also of how the interior reacts to the environment. Jupiter and Saturn adapted by accumulating gas on a colossal scale. Uranus and Neptune, exiled in the cold, adapted by transforming simple chemistry, water, methane, ammonia, into exotic states of matter we don't see anywhere else in the solar system. They are worlds where climate is governed more by internal physics than by solar energy, and where, literally, diamonds can fall from the sky. After traveling through the chaos of planetary formation, from the collapsing nebula to rocky cannibalism, from the giant's migration to the exotic chemistry of the exiles, we finally reach the end of the line, where construction stopped, where gravity, time, and matter simply ran out. This frontier is not marked by a majestic planet or an ice giant, but by a diffuse and fragmented region known as the Kuiper belt. Here, material density fell to such critical levels that the accretion processes that created all previous planets simply had no chance of working. The Kuiper belt begins approximately where Neptune's orbit ends, at about 30 astronomical units from the Sun, and extends to 50 AU. It's a vast region, equivalent to the entire inner system in radius, but containing less mass than Earth itself. For context, Earth's region had enough raw material to form a planet of one Earth mass in a few million years. In Jupiter's region, ice tripled that amount. But in the Kuiper belt, the protoplanetary disk surface density was less than 0.01 Earth mass per AU2, a cosmic desert in comparison. This scarcity was not accidental. It results directly from the previous migrations. When Neptune was hurled outward during the NICE model, it crossed this region like a gravitational tractor, scattering planetesimals in all directions. Many were ejected into interstellar space. Others were captured in orbital resonances with Neptune, like the famous objects in 3-2 resonance, including Pluto. What remained was a rarefied population of icy bodies, the Kuiper belt objects, KBOs. These objects are composed mainly of water ice, methane, and ammonia, with crusts of reddish organic materials formed by solar radiation. Unlike asteroids in the inner belt, which are rocky, KBOs are icy leftovers, exactly the type of material that should have coalesced to form new ice giants. But the density was too low. For two planetesimals to meet and collide, they would need to wait centuries or millennia between encounters. And even when they collided, relative velocities were too high due to Neptune's perturbations, resulting in fragmentation instead of accretion. Pluto is the perfect example of this construction failure. With only 0.0002 Earth masses, 1/500 of Earth's mass, Pluto is a planetary embryo frozen in time. It never had a chance to grow to become a miniature Neptune. Benaudide, its complex surface, with plains of frozen nitrogen, mountains of water ice, and a tenuous atmosphere that sublimates and condenses seasonally, shows it is geologically active, but on a minuscule scale. Pluto even has 5 moons, with Charon almost half its size, suggesting it was born from an impact similar to the one that created our moon. But without enough ambient material, it remains stuck in this incomplete form. The Kuiper belt is not homogeneous. It's divided into regions. The classical belt, stable orbits little perturbed. Resonant objects, captured by Neptune like Pluto. The scattered disk, eccentric orbits, scattered by Neptune's migration. And the mysterious unknown belt beyond 50 AU. This truncated structure, the cliff at 50 AU, is a direct signature of Neptune's influence. It swept everything beyond this limit, leaving a void marking where its migration stopped. Here, planetary construction effectively ended. Not for lack of time or gravity, but for lack of raw material. What remains are thousands of potential Plutos, worlds that began the journey but never reached the destination. They orbit silently, preserving the original solar nebula's chemical composition. Mute witnesses to the point where the solar system exhausted its constructive resources. But the beyond doesn't end here. Something even larger lurks in the darkness, an almost spherical shell of comets marking our system's true limit. The Oort cloud. At the end of the solar system's construction line, where raw material ran out and Pluto was stuck as a frozen embryo, we might expect only silence and stagnation. But even here, in the icy darkness of the Kuiper belt, geology didn't stop. These remote worlds defy the idea that cold built dead. They pulse with internal heat, powered by primordial processes persisting billions of years after formation. The most impressive example is Pluto, which reveals a geologically living heart beneath its frozen nitrogen crust. When the New Horizons probe flew by Pluto in 2015, it revealed a world much more dynamic than models predicted. The surface exhibits Sputnik Planitia, a glacial plain 1,000 kilometers in diameter, smooth as a mirror and full of frozen nitrogen blocks floating in a sea of ice. This plain is not static. It is geologically young, less than 1 million years old. Thermal convection in the subsurface pushes ice blocks to the surface, continuously rearranging it. Pluto is not a fossil. It is a world in renewal. This dynamism comes from cryovolcanism, volcanism with icy materials instead of molten rock. In Pluto's interior, radioactive decay of elements like uranium, thorium, and potassium-40 generates residual heat. This energy heats an internal mantle of water, ice, and rock, creating a liquid salty ocean beneath the outer crust. Pressure and heat make this mantle convect, like Earth's mantle moves tectonic plates. Bubbles of cryomagma, a mixture of ammonia, water, and methane, rise to the crust, where they erupt like cryogenic geysers. The mission revealed water ice mountains 3 to 6 kilometers high, taller than the Alps, supported by ice's rigidity under low temperatures. And there are active cryovolcanoes, like those in the Right Mons region, which expelled nitrogen compounds a few million years ago. This internal heat keeps Pluto geologically alive, even receiving 1/900 of the sunlight reaching Earth. Charon, its largest moon, shows plains reddened by organic compounds transported by a solar wind from Pluto, evidence of active atmospheric interaction. Other KBOs share this vitality. Ceres, almost Pluto's size, has a bright surface suggesting recent cryovolcanism. Haumea, elongated like a cigar, spins so fast, 4-hour period, that it may expel ice in an equatorial ring. Even Makemake shows signs of fresh methane. These worlds are not dead. They evolved slowly, with internal heat sustaining geological cycles that can last billions of years. This heat defies expectations. Far from the sun, energy comes from within, not from outside. Radioactive decay, combined with tidal energy, in binary systems like Pluto-Charon, maintains subsurface oceans and cryogenic volcanism. It's life in the ice. Persistent geology where planetary construction stopped, but remodeling continues on eternal timescales. The Kuiper belt marks the end of planetary construction, but not the end of the solar system. It ends abruptly at 50 AU, giving way to the Oort cloud, an almost perfect sphere of trillions of icy comets enveloping the entire system like the shell of a cosmic egg. This structure marks where the sun's domain ends and true interstellar space begins. The transition is defined by the Heliosphere, the protective bubble sculpted by the solar wind. The sun is not passive. It expels a constant flow of charged particles, protons, electrons, plasma, at 400-700 kilometers s. This solar wind creates dynamic pressure that pushes the gaseous interstellar medium outward, forming the heliosphere, an elongated bubble 120 AU in diameter in the direction of the sun's movement through the galaxy. Inside it, solar plasma dominates. Outside it, interstellar plasma takes over. Voyager 1 in 2012 crossed the heliopause, the tenuous boundary, at 121 AU, confirming the transition. Solar plasma noise ceased. Galactic cosmic particles exploded. The Oort cloud begins just beyond, at 2,000-5,000 AU, extending to 100,000 AU, 1.6 light-years, almost halfway to the nearest star. It's not a flat disk like the Kuiper, but a spherical shell, the result of isotropic dispersal of planetesimals during the giant's migrations. Trillions of icy comets orbit the sun in highly elliptical and inclined trajectories, tilted in all directions. Their total mass may equal several Earths, but density is minuscule, 1 comet per cubic stellar system. This cloud is the final stock from construction. Planetesimals ejected by Neptune's migrations and by the fifth giant or other events were scattered into distant orbits, but still gravitationally bound to the Sun. Occasional perturbations, passage of nearby stars, encounters with the galactic Smith cloud send some toward the Sun, creating long-period comets like Hale-Bopp. These visitors bring pristine samples of the solar nebula, explaining deliveries of water and organics to primitive Earth. The heliopause separates these icy worlds from interstellar void. Inside the bubble, the Sun reigns. Outside, galactic radiation and interstellar plasma dominate. The Oort cloud is the system's shell, fragile, sparse, but defining. It marks where solar gravity beats escape, containing the remnants that never coalesced. It's the true beyond. Not empty, but filled with icy ghosts orbiting in eternal twilight, awaiting a perturbation to tell their story. At the Oort cloud's edge, where solar gravity barely maintains its influence, something strange happens. 6 distant objects from the outer Kuiper belt, known as extreme trans-Neptunian objects or ETNOs, exhibit curiously aligned orbits. Their extremely elongated ellipses don't point in random directions, as expected in a dynamically relaxed system. They converge toward the same point in the sky, as if something invisible were shepherding them. This anomaly is not coincidence. It suggests the presence of a massive body orbiting at 400 to 800 AU, hypothetically dubbed Planet 9. The evidence is purely mathematical. In 2016, Konstantin Batygin and Mike Brown from Caltech analyzed these ETNOs' orbits and found a statistically improbable pattern. All their lines of apsides, the orbit's most distant point, are clustered within a cone of only 10 to 20 degrees in the sky. In a system without external perturbations, orbits should be randomly distributed across 360 degrees. The probability of this alignment occurring by chance is less than 0.0007%. Something is forcing these orbits to align. The mathematical model explaining this is simple but powerful. A planet with 5 to 10 Earth masses, a super-Earth, orbiting with a period of 10,000 to 20,000 Earth years, exerts enough gravitational influence to guide the ETNOs over billions of years. Its gravity doesn't tear them from their orbits, but subtly pushes them, keeping them aligned with its own orbit. It's like an invisible shepherd, using only its gravitational staff to keep the flock cohesive. How would this Planet 9 have been born? The most likely hypothesis connects it directly to our thread. It's a native survivor from the solar system's outer region. While Uranus and Neptune were hurled away during the NICE model, Planet 9 may have formed even farther out, in a region where material density was low but sufficient to create a large, rocky, icy core. It never participated in the inner giant's chaotic migration because it was born already in exile, beyond Jupiter and Saturn's direct influence. Alternatively, it may be one of the many embryos that the sacrificed fifth giant scattered during its ejection. Instead of being launched into interstellar space, Planet 9 may have been captured in an extremely elliptical orbit, circling the Sun at colossal distances. Its orbit would be so eccentric that it would spend thousands of years in the darkness of the outer Oort cloud, invisible to current telescopes, before approaching again. The search for Planet 9 continues. Telescopes like the Vera C. Rubin Observatory, under construction in Chile, will systematically sweep the sky starting in 2025, covering regions predicted by the model. If confirmed, it would rewrite our understanding of planetary formation. The solar system didn't end with Neptune. There's a 9th planet hidden in the twilight, shepherding the remnants of primordial construction. With Planet 9 as a possible guardian of the shadows, it seems we've reached the end of the solar system formation story. But this is an illusion. The system we've built throughout these blocks, from the collapsing nebula to the icy exiles, is not a final and eternal state. It's merely a transitory phase, a dynamic equilibrium doomed to be broken. Gravity, which built everything, also guarantees destruction. The planetary cycle doesn't end with formation. It continues through relative stability and, inevitably, dissolution. Even now, 4.6 billion years after the nebula's collapse, the system still oscillates. Mercury's orbit is particularly unstable. Its eccentricity, already slightly elliptical, suffers subtle perturbations from other planets, especially Jupiter. Long-term simulations show that in about 3 to 5 billion years, there's a 1% chance Mercury will be completely ejected from the solar system, collide with Venus, or even fall toward the Sun. This instability is not a defect. It's the signature of a young system, still adjusting after the chaos of the giant's migration. On even larger scales, the entire system's fate is sealed by the Sun's aging. In approximately 5 billion years, the Sun will exhaust its central hydrogen and begin the red giant phase. Its luminosity will increase 2,000 times, swallowing Mercury's and Venus's orbits. Earth, at the edge of the destruction zone, will face boiling oceans, lost atmosphere, and melted surface. An echo of primitive Venus's fate, but on a stellar scale. Jupiter may survive, but will be dragged inward, becoming a scorching, hot Jupiter. Surviving planets will be transformed. Jupiter's and Saturn's icy moons will have their subsurface oceans boiled. The Kuiper belt will be vaporized. The Oort cloud will be partially destroyed by solar expansion. After the red giant, the Sun will eject its outer layers, forming a planetary nebula and collapse into a white dwarf. The exposed, cold, dead core, orbited by a skeletal system of charred planets. But even until this end, dynamics continue. Before the red giant, there are billions of years of orbital evolution. Mercury may oscillate enough to trigger chaotic resonances with Venus and Earth, potentially colliding or ejecting planets. Jupiter will continue cleaning comets from the Oort cloud, altering its distribution. Planet 9, if it exists, may be perturbed and ejected, or capture new objects in its resonances. This future instability mirrors the violent past. Formation was not a single event. It was the first act of a 13-billion-year drama, the Sun's total lifetime. The second act is the relative stability that allows life. The third will be destruction. The solar system is dynamic by definition. The same set of physical laws that built it guarantees it will never stand still. When we look at the night sky, we see not a complete and eternal system, but a fleeting moment, a fragile balance between creation and annihilation. Mercury oscillates today as it oscillated billions of years ago. Pluto pulses with cryovolcanism while awaiting its end. Planet 9, if real, shepherds Etnos in darkness, oblivious to the Sun's fate. We are witnesses to a story that began with a supernova and will end in a planetary nebula. Formation was merely the prologue. The eternal cycle, construction, equilibrium, destruction, is the complete narrative. Of all the planets in the solar system, Uranus is the strangest. Not for its composition or size, but for the way it spins. While all other planets spin like tops with their rotation axes approximately perpendicular to the plane of their orbits, Uranus lies on its side. Its rotation axis is tilted 98 degrees relative to the orbital plane, practically horizontal. This means that instead of spinning upright like Earth, Uranus rolls through space like a ball along its orbit. During half of its 84 Earth-year year, one pole faces directly toward the Sun, bathed in continuous light. During the other half, the opposite pole faces the Sun, while the first remains in total darkness for decades. This extreme tilt cannot be a natural result of formation. When planets form from rotating disks, they naturally acquire rotation in the same direction as the disk, with axes approximately perpendicular to the orbital plane. Something had to knock Uranus down, and the most accepted explanation is brutal. Uranus was struck by a massive object during or shortly after its formation, probably during the chaotic phase of the Great Migration described by the NICE model. To tip over a planet the size of Uranus, 14.5 Earth masses, 4 times Earth's diameter, the impactor needed to be gigantic. Simulations suggest that an object with at least 1 to 3 Earth masses, approximately the size of Earth or even larger, collided with Uranus at a sufficiently oblique angle to transfer angular momentum without completely destroying the planet. The impact may have occurred in two scenarios. Either Uranus was struck while still forming, or it was struck during chaotic migration, when multiple planetary embryos and orphaned cores were being hurled through the outer system. The second scenario is more likely. During the resonant instability that expelled Uranus and Neptune, the system was full of stray bullets, planetary embryos that couldn't coalesce into complete planets, rocky, icy cores ejected from their original orbits, and even potentially a fifth giant, which we'll discuss later. Uranus, on its chaotic journey through the planetesimal disk, had a devastating encounter with one of these objects. The impact not only tipped Uranus over but also had other profound effects. First, it would have generated enormous heat, vaporizing part of the icy mantle and potentially further differentiating the planet's interior. But curiously, Uranus didn't retain this heat. As mentioned before, Uranus radiates very little internal heat, unlike Neptune, Jupiter, and Saturn, which all emit more energy than they receive from the Sun. One theory suggests the impact may have restructured Uranus's interior in such a way that it created an insulating layer, preventing efficient heat flow from the core to the surface, trapping thermal energy deep inside the planet. Second, the impact may have affected Uranus's magnetic field. While other giant planets have magnetic fields aligned approximately with their rotation axes, like Earth, Uranus's magnetic field is displaced and dramatically tilted. It's not centered on the core and is tilted 59 degrees relative to the rotation axis. This suggests that the internal convection generating the field was perturbed, possibly by the giant impact that mixed internal layers that would normally remain stratified. Third, and perhaps most intriguing, the impact may have ejected material that reaccreted to form some of Uranus's moons. Uranus has 27 known moons, and the 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, orbit in the planet's tilted equatorial plane. This is strange. If Uranus was tipped over after the moons formed, we would expect the moons to remain in their original orbital planes, not following the planet's tilt. But they do follow. This suggests that either the moons formed after the impact, from ejected debris, or the impact was so powerful that it reoriented the entire moon-planet system as a unit. Life on Uranus today reflects this ancient trauma. The seasons are extreme and bizarre. When one pole points toward the sun, it heats significantly, while the other pole freezes in darkness. But surprisingly, Uranus doesn't show large temperature differences between illuminated and dark poles. This suggests the atmosphere redistributes heat very efficiently, perhaps through powerful winds circulating the planet, balancing temperatures. Still, Uranus's climate pattern is the strangest in the solar system, shaped by the sideways rotation that is the permanent scar of one of the most violent events in planetary history. Uranus, then, is more than a distant ice giant. It is a living relic of the Great Migration's chaos. It was born in violence, was thrown into darkness, and midway was struck so hard that it was permanently marked. Its sideways rotation is a reminder that solar system formation was not a delicate and predictable process, but a series of catastrophes from which only the lucky or the resilient survived. When we think the giant's story is already complicated enough, modern numerical simulations add one last character to the plot: a fifth giant. We're not talking about a dwarf planet or marginal body, but a complete ice giant, similar in mass to Uranus or Neptune. It would have been born along with them, participated in the nice model's chaotic dance, and in the end been expelled from the solar system as a definitive exile. Why imagine a planet we don't see? Because computer models that attempt to reproduce the solar system's current configuration, giant positions, eccentricities, inclinations, Kuiper belt and Oort cloud structure, work much better when we add an initial fifth giant. In scenarios with only 4 giants, simulations often produce problematic results. Jupiter ends up too close to the Sun, Uranus or Neptune are ejected, or the Kuiper belt ends up with an orbit distribution incompatible with what's observed. When we add a fifth giant, something curious happens. Suddenly, the results impressively approach the real system. The idea is this: In the initial arrangement, Jupiter, Saturn, Uranus, the fifth giant, and Neptune were in relatively compact orbits, all within approximately 15 to 20 astronomical units. The fifth giant occupied an intermediate position between Uranus and Neptune, or perhaps more external. It was another player in the network of resonances and energy exchanges with the planetesimal disk. When the resonant instability between Jupiter and Saturn exploded, as we saw, the entire system entered chaos. Uranus and Neptune were hurled outward, crossing the planetesimal disk and scattering ice everywhere. In this process, the fifth giant ended up in the wrong place at the wrong time. It had very close gravitational encounters with Jupiter, the most massive planet. In dynamical terms, this is dangerous. Jupiter functions as an extremely efficient gravitational sling. In one of these close encounters, the fifth giant was literally launched outward. By the laws of energy and momentum conservation, when a light body passes very close to a very massive body, it can gain an enormous amount of orbital energy at the larger planet's expense. Jupiter loses a bit of energy, migrating slightly inward, and the smaller body gains enough velocity to completely escape the Sun's gravity. It's the same principle used in space probe maneuvers, but here applied on a planetary scale. The result? The fifth giant was ejected into interstellar space, becoming an orphan planet, wandering alone among the stars, without a parent star. This dynamic sacrifice brought stability to the remaining system. Without this extra planet perturbing the orbits, Uranus and Neptune could settle into stable positions. The Kuiper belt could reorganize, and the current architecture emerged. In other words, the solar system we know, with 4 giants in current orbits, is in part a consequence of a fifth sibling who paid the maximum price, being expelled forever. This idea fits well with an interesting fact from modern astronomy. We've already detected indirect signs of many floating planets without a star in the galaxy. Their formation can largely be explained by processes like this. In other words, the fifth giant story is not an isolated fantasy. It may be a common chapter in the biography of many planetary systems out there. We are the system that survived with 4 giants at the cost of expelling a fifth. Our current equilibrium is literally the result of a loss.